Right, today's conversation will be focused effectively on main types of compounds. We're going to learn the difference between ionic compounds and covalent compounds. And we're also going to talk about different forces, different interactions that hold atoms and sometimes molecules together. So first of all, let's give the brief definition. First definition of an ion. An ion is formed when an atom either loses electrons, which results in the ions that are charged positively, because remember the nucleus will still have same number of protons, but the number of electrons will be lower, so positive and negative charges will not be balanced. Or, if they gain electrons, in this case, the number of negative charges will be greater than the number of positive charges, and that will be a negative ion. As we discussed, I believe, last week, positive and negative charges attract. And they attract very strongly. So when these ions attract, the bonds that are formed between them are called ionic bonds. So overall, compounds can be divided into ionic compounds, the ones that consist of ions, and molecular or covalent. So the bonds that are formed between atoms in covalent compounds, surprisingly, are called covalent, and we will have a chance to discuss how they formed. Now, a couple of examples of covalent compounds are, for instance, water and propane. And without going into the details why we describe water, why we have, how to say this, without going into any details, water is a polar covalent molecule, while propane is non-polar. We will talk why. So bonds between the atoms are formed because of electrons. So what can happen? If atoms lose or gain the electrons, they become ions. Does that make sense to you folks? Okay? So therefore, when we talk about ions, we talk about ionic bonds formed between them. Covalent bonds are formed when electrons are shared. So we will have a chance to discuss this, but if you would look at the periodic table, all elements, without any exceptions, have less than 8, or 8, no more than 8, let's put it this way, no more than 8 electrons on the outer shell, which actually brings us to a very important and very short conversation about the structure of an atom. Okay? Remember the image that we saw when you have like a nucleus, right? And the electrons circling around. So this is called a planetary model of atom. It was proposed by Niels Bohr in early 20th century. But most important thing is that you can compare an atom to a solar system. So for example, if we would look at the atom of lithium, which is an element number 3, second period, first group, its nucleus, I'm going to put a letter N, will contain how many protons? 3, yes. And considering that we're talking about lithium 7, how many neutrons then? 4. How many electrons should it have? 3. So, turns out that when you form the first orbital, the first layer of electrons, and it's some pretty crazy quantum physics which I am not competent at all to talk about. The first orbit, we call it orbital, will contain 2 electrons. And then there's going to be a second orbital, which will contain 1 electron, so total of 3. Does that make sense? So I have 2 electrons. I call them, in my opinion, to understand it easier, think of it as an apartment building. So on the first floor, only 2 electrons can leave. Okay? And on the outer floor, outer orbital, the number of electrons cannot be more than 8. It can be less, like in case of lithium, but it can't be more than 8. I'm going to give you another example just for comparison, same period, but different atom. So I'm going to use this image. So fluorine, with its atomic mass of 19, okay, also has 2 orbitals. How many protons does it have? Neutrons? 10. Remember, first orbital can only have 2 electrons, right? How many more electrons do we have to place? 7, yes, 7 electrons. So 1, 2, I'm just randomly, 3, 4, 5, 6, and 7. So fluorine has 7 electrons on the outer shell. Does that make sense to you? So far, this is just, if you will start asking me questions, why it is, like why an atom, quote unquote, prefers to have 8 electrons on the outer shell, as a revenge, I will send you to read some quantum mechanics book. I have no idea, don't ask me. I passed quantum mechanics, and I literally mean I passed it. I don't remember anything. Okay? The point is, you want, for the greatest stability on the outer shell, there should be 8 electrons. It can be achieved through sharing electrons or stripping, losing, gaining. Okay? Does that make sense? So, couple of fairly easy tricks. Okay. For main groups, I'm going to put the parentheses 1, 2, and 13 through 18. Do you follow? Okay. Generally speaking, number of electrons on the outer shell is 1, 2, 3, respectively. Does it make sense? So if you want to know how many electrons on the outer shell of an atom of bromine, element number 35, you look for the number of the group. What is the number of the group for bromine? 17. Well, you have to subtract 10, but even if you count from like 1, 2, then 3, 4, 5, 6, 7 electrons, does that make sense? I can't emphasize enough that groups 3 through 12, they are transitional elements. They do not follow rules. Am I making sense? Believe me, I will never ask you to identify, just to know what is the number of electrons on the outer valence shell in, say, manganese. Am I making sense? But if I ask you how many electrons on the outer shell of carbon, element number 6, what do you tell me? 4. Do you understand what we did? If not, let me know right now.
I don't know.
Okay. Okay, perfect. Let's do it. Group number 1. How many electrons on the outer shell? 1. That's a rule, okay? Sorry, I can't see you, so I have to lean over. In a group 2, how many electrons? 2. Then we're skipping 3 through 12. Just skipping. Just ignore them. Group 13, how many electrons? 3. Group 14. Keep going. 4, 15, 16, 6, 17, 18, 8. Group 18, does that make sense? I'm subtracting 10. Yes. For groups 13 to 18, I subtract 10. Okay? So group 18 is noble gases. They don't react with anything because they already have 8 on the outside shell, on the valence shell. They're fine. They don't need any more electrons. Does that make sense? Now, for all elements, number of electron orbitals equals period number. So if you want to know how many orbitals with electrons bromine has, you look at which period he's located in. And this period is number 4, this 4th line. Do you see bromine, number 35? It's 4th line, 4 shells. So the 4th shell, the outer shell, is the valence shell. Now, if you look at the periodic table that we have in the class, on the right-hand side of noble gases, you can see tiny little numbers like 2 and then 2 and 8, then 2, 8, 8. Can you see that? So helium is the lightest noble gas. It has only one shell because it's in the first period, and that shell has 2 electrons. That's the only exception from octet rule. Does that make sense? You move down to the period 2. Do you follow? Neon has 2 orbitals. Can you see that? The first has 2, the second, the outer, has 8. Argon has 3. The first has 2, the second and third have 8. Am I making sense? So in terms of in the boundaries of this course, we barely touch on the reasons, on the logic, how the shells are filled. Because there are certain rules how you can do it pretty much. But we're not doing that. There will be nothing like that on the exam because it goes more towards general chemistry rather than this class. Am I making sense? Now, let's go back to our compounds, ionic and molecular. So ionic compounds are always formed by a metal and non-metal. No exceptions. So there's a metal, there's a non-metal. Okay? Do you follow? It's not an element. Just M stands for metal, and M stands for non-metal. Okay? So let's say our metal is sodium. Sodium, which group does it belong to? The column. Group. Na, sodium. The column. 1. Sorry, I misheard. 1. How many electrons on the outer shell then? 1. Chlorine, which group does it belong to? 17. For, 2 digits, what do you need to do? Subtract 10, so how many electrons does it have? There you go, 7 electrons. In order to reach the magic 8, it's quote-unquote easier for chlorine to get 1 electron than to lose 7. Does that make sense? Just, like kind of common logic. Does that make sense? I try to apply human logic to the behavior of electrons. They don't have brains. They don't have a lot. But think about from the standpoint of energy. What's easier to strip? 1 electron or 7 electrons? 1. So this 1 electron will be stripped of sodium. Does that make sense? And it will be stripped by chlorine, which will add this electron, forming the magic 8, the octet. Now, chlorine anion is stable. Does that make sense, everybody? Sodium, on the other hand, loses that 1 electron on the outside. But when you look at periodic table, can you tell me which period does sodium belong to? 3, which means it has 3 shells. Look at argon in the same period on the very, very right. Okay, do you see argon? So if sodium, don't do anything so far. If sodium loses that 1 single electron on its outer shell, this shell effectively doesn't exist anymore. Makes sense? It's empty. Shell is not a physical space, it's a concept. So if you strip the 3rd shell, how many electrons are on the 2nd shell of all elements of the 3rd period? Look at the tiny black or whatever numbers on the right. 8. Look, 3rd. You're looking at the 4th. Look at the 3rd period. 8, right? Does that make sense? So it means that sodium lost that single electron, and now the outer shell has 8. Okay? We'll get back to this and double illustrate it again. Okay? Molecular bonds, covalent bonds, molecular compounds formed by nonmetals. And in this case, they share electrons. So this sharing allows each of them to have 8 electrons on the outer shell effectively. There's an overlap. Don't worry, if something seems confusing, first of all, it should. And second, we will talk more about that. Okay?
Yeah, because is this going to be on the exam?
Yeah. Yes, that will be on the exam. So we're going to start with a conversation about, hang on, we will return to this many times today. Okay? So first of all, we are focusing on sort of like true metals. okay, which are in the group 1A, or just group 1, group 2, and group 13. Okay, make sense? Now, for group 13, specifically, and this is very important, we're not talking about each and every element in this group. It is aluminum. Okay? So, elements of the group 1A, how many electrons do they have in the outer shell? Group 1. Elements of group 1, 1 electron. Elements of group 2, how many electrons do they have in the outer shell? 2. Aluminum, well, all elements of group 13, but specifically aluminum, how many electrons in the outer shell? 3. Okay? For these guys, losing electrons is easy. Does that make sense? So they need 8. They need stable. Losing 1 or 2 or 3 is fairly easy. Simple question, purely common sense. What is easier? To lose 1 electron for sodium, to lose 2 electrons for magnesium, or 3 electrons for aluminum? 1 for sodium, yes. Does that make sense? Now, they lose the electrons and become positive ions. Okay? So this is sodium, and I'm gonna do slightly different illustration here, okay? So we have sodium nucleus, which contains how many protons? Sodium's number 11. 11 protons, perfect. How many neutrons? 23. The mass is 23. 12, yes. Okay, so sodium, 11, 23. How many electrons then? 11. How many shells? 3. So I'm not going to draw the entire shell, okay? Shell 1, shell 2, shell 3. So first shell is filled. Look at the first period. What is the maximum number of electrons on the first shell? 2. Second shell, how many electrons does it have? No. Second shell, because sodium is in the third period. So second period, look at the second period at the very right, neon. Do you see the numbers 2 and 8? 2 is the first shell, 8 is the second shell. How many electrons do we have so far? 10. We need to add 1 more. Does that make sense? So the distribution of electrons in the atom of sodium is 2 on the first shell, okay, because this is the max. 8 on the second, and 1 on the third. All good? No? What is unclear? Because I don't know. If I don't know.
And this is one time.
Okay.
Just one time. Okay.
So
I just need to know where you're at.
Sure. Sure.
So you said you over here at 11, like you said you over here?
No, it's a group number. This is sodium, yes.
So you're right here?
Yes.
So you said protons is going
11. There are 11 protons because
going that way.
no.
Subtracting.
I'm not sure what you're asking because this is not what I was saying. What I was saying is that the elements of the third period, that's the row, have 3 shells. That's it.
Okay.
These are, right here, shells.
Mm-hmm.
We also mentioned that the elements of the first group, the column, have 1 electron on the outer shell. since just one electron, the number of the group, which is 1. So total number of electrons must match the number of protons, which is 11. So sodium will have total of 11 electrons, 1 on the outer shell, and then we need to put 8 and 2. If you would look at the very right of the periodic table, the entire table, neon is the previous noble gas that goes before sodium. It has all shells filled. The first shell contains 2 electrons. I don't know. No. Neon, I doubt that neon would start with Li. Neon starts with Ne, the previous noble gas. Yes, it's 10. I was talking about the group 18 being noble gases multiple times. Neon has 2 electrons on the first shell. It's a small number on the right-hand side, and 8 electrons on the second. So this is how many electrons sodium will have on the first and second shell. And this is what the image on the slide right now that I just drew reflects. Shell number 1. Here. Folks, I can't stress enough. Pay and just watch, pay attention, because if you distracted for a minute, then the logic is lost.
It's too fast.
I would argue otherwise. So
It's too fast.
magnesium, okay, number 12, right? So we have 12 protons, okay, which means we got to have 12 electrons, right? So if this is the nucleus, if you find magnesium in the periodic table, which period is it in? 3. So how many shells? Now that you know to look at the previous noble gas, what is the noble gas that has a number lower than magnesium? Right, again, neon, right? Because if you go backwards, it's the first noble gas that you encounter, yes.
Noble gases are red.
Say again?
Are noble gases on period?
8 on group 18, yes.
Oh, they're just
All of them are noble gases, yes. What was the question, sorry?
you always look.
So you look back, yes, you go back and you look which noble gas is before, yes. So for these metals, for aluminum, group 1, group 2, okay, so go back. The gas that is before is neon, okay? Neon has 2 on the first, 8 in the second, and we need 2 more because magnesium has 12 protons and has to have 12 electrons, so we add 2 on the outer shell. Does that make sense? Now, I'm going to add one more example right here. And we're just going to do potassium. Okay? So, potassium, number 19. So, how many protons? 19 protons, right? Because it's a group number, element number, atomic number. How many electrons then? 19 electrons. So which period is it in? 4th. So how many shells? So now I want you to identify the previous noble gas. Argon, right? Does that make sense? You go backwards. Potassium's 19 and go back. Argon is 18. How many electrons does argon have on the first shell? On the second? On the third? So what's so far, what do we have total? Dude, 18. Come on. 8 plus 8 plus 2, it's 18. We need 19 total. There you go. And we kind of lost a little bit the forest behind the trees, because my goal here was this. Check it out. Oh shit. Check it out. What the? Sorry, I'm trying to. Okay, I can't use the eraser. I'm sorry. So if potassium loses that one electron, this shell's gone. Does that make sense? This becomes its outer shell. 8. It's happy. Does that make sense? If magnesium loses 2 electrons on the outer shell, it has 8. It's happy. Go ahead.
So it would still be considered magnesium? It wouldn't be different? It would be the previous element?
Say it one more time.
So will it still be magnesium even though it lost the...
Excellent question. Yes, it will still be, as an element, it's magnesium. But we would say that it's a magnesium ion with 2 positive. Remember, it's all about protons. If protons are the same, it's the same element. Magnesium is still magnesium. Losing electrons is a chemical process. It happens, this is what happens in chemical reactions. The movement of electrons, quote unquote. If we start changing the number of protons, it can be done. Those are nuclear reactions. Like when an atomic bomb explodes or some other stuff happens. We're going to talk about it in Unit 5. But so far, does that make sense? It's not the end of the examples. We're going to have a ton more. So, quick thing without writing. Let me finish and then I will answer your question, okay? Find calcium. Number 20. Hold on, don't tell me anything. Calcium, 4th period. The only thing I want to ask you is, what is the noble gas that you need to refer to? Argon. That makes sense? You go back. Barium. What is the noble gas that you need to refer to? You can tell me the number of the element. Say again? He. No. Okay, my bad. Barium, number 56. My bad. Xe, yes. Thank you very much. Perfect, yes. Barium, number 56, 6th period, second from the left. Do you see that? When you start going backwards from barium, you hit xenon, Xe. Does that understood? This is how you go. I'm reminding you, you can write it down. This rule, going to the previous noble gas, applies to group 1, group 2, and group 13. Okay, let me write it down. Groups 1, 2, 13. Go to previous noble gas.
Why? Why only 1, 2, 13?
You'll see. Just wait. Just wait. I don't want to confuse, like, for now, does that approach make sense to you all? Yeah? Okay. Because we're going to talk about nonmetals now, and you will see why it's applied only to 1, 2, and 3. Okay?
Okay, before we go too far, I guess the only thing I'm getting stuck on is that you were saying that the transitionals are 3 through 12.
Correct.
And that with those, we're not.
Just ignore them. We're not.
We're ignoring them.
You're ignoring those.
But with the protons and neutrons, you're saying.
That's a completely different story.
Right, but you guys are adding and plusing or minusing, like, for potassium.
Yes.
The proteins minus 10.
What do you mean minus 10? I don't understand what you say by minus
I
10.
didn't know where you're getting the numbers from.
Which numbers? Exactly.
I don't know the protons and the
Protons? Last week we talked about the fact that the atomic number, 19, reflects the number of protons.
Right.
That's it. That's where we're getting protons from. It's 19.
I remember, but I don't know. I thought y'all were like subtracting. I don't know.
And then if you're referring to neutrons, we need to take the atomic mass, which is for potassium is 39, okay, and subtract atomic number. So we have 19 protons, right? And then we have 20 neutrons, because we need to subtract 19 from 39. This is how we find the number of neutrons. So the mass number is 39. I told you, remember that number on the bottom in red? You need to round it, either down or up. And you will get the mass number for the most common, quote-unquote, version of an atom. Okay? And in our calculations, this is how we're going to do it. So if I ask you to find the atomic mass or mass number for barium 56, what will be the atomic mass for barium? 56 is not the atomic mass.
137, right?
130, you round, it's a rule of rounding. 56 is the atomic number, and look at the bottom, you see the number 137.327?
Right.
If I ask you to round just that number, without any reference, you would round it down
Right, 137.
to 137. That's it. Does that make sense?
Yeah.
So that's how you figure, like yttrium, number 39. What's the atomic mass that you will be using, if ever? 89. Yeah. Does that make sense? Cool. Okay. Yes.
So for magnesium, and when you just rewrote it for, the Mg, 2 positive.
It lost 2 electrons, yes.
Right. So are you writing the 2 positive because it still has 2 outer shells?
No. So how many protons does it have?
8, right? It's supposed to have 12.
12. After losing 2 electrons, how many electrons does it have? So you have 12 pluses and 10 minuses. Only 10 pluses. So you have 12 protons in the ion. Okay? So magnesium ion has 12 protons, agreed? But only 10 electrons. Okay? So if you have 12 with a positive sign, and you have 10 with a negative sign, what is the result? Better sense? Cool. Okay, nonmetals. 15, 16, 17. They accept electrons. How many electrons do elements of the group 15 have on the outer shell? $15. What do you need to do? Subtract 10, so 5 electrons. What about group 16? 17? Okay. So you see, now, taking away 5 electrons is very hard. Taking away 7 is even harder. This is why these elements gain electrons. Okay? Am I clear? And that happens, now you're familiar with noble gases, until they have as many electrons on the outer shell as, can't emphasize it enough, nearest noble gas. To make the matter simple without writing anything, look at the periodic table, look at element chlorine, number 17, and tell me which noble gas is the closest. Argon. It's next, right? It literally is next. Now look at the element oxygen, number 8. What is the closest noble gas? Noble gas, closest noble gas. Neon and E. Does that make sense? So the idea is that it's got to be closest. So hear me out. Just hear me out. The number of the atomic number of oxygen is 8. Sorry. Do you agree with me? The atomic number of neon is 10. Do you agree with me? So, the atomic number of helium is 2. Remember, the periodic table is basically line after line of elements. Am I clear? So if you need to go from oxygen to neon, you have to make 2 steps. Does that make sense? 1, 2, and you're there. If you have to go from oxygen to helium, you have to make 6. Neon is farther. Does that make sense? So, 1, 2, and 3, 15, 16, 17. You may ask, what about groups 13 and 14? They weird. Let's not what about group 14? Let's not mention it for now. We'll get there. It's not hard. Just go ahead. Question?
No question.
Okay? Makes sense, right? So, let's take a look at the simplest example. Chlorine. Okay, we're going to do the same description because the repetition is, there's a Russian saying, repetition is the mother of learning. Okay? So, chlorine. Sorry, it's weird behavior. What is the atomic number for chlorine, Cl? What is the mass number? 35. 35. There are people that will help you out if you can't see the number. 35. So let's write down some basics. How many protons? How many neutrons? How many electrons? 17. Before we move on, any questions about that? Okay? All good. Nucleus? Okay, nucleus. How many shells, electron shells, does chlorine atom have? Huh? 3. Does everybody understand why it is 3?
Yes.
Yes, because it's a third period, third line, yes. 3 shells, perfect. Okay?
Catching up.
That's good. That's good. So, remember, the outer shell is the one that does not have an octet. Previous ones, they filled. How many electrons max can be on the first shell? About second. How many electrons do we have in total right now? We need to accommodate 7 more. They go on the outer. Does that make sense? Now, we figured that it is in this situation, taking away 7 electrons is really hard. Make sense? Like, they vary tight. It's much easier from energy standpoint for chlorine to quote-unquote steal an electron. Am I making sense? So if it steals an electron from another atom, let's say it's sodium, okay? You're going to add an electron here. What you're going to have chlorine, the nucleus, right? 3 shells. Now you're adding 1 electron to 7. What is the final number? So how many electrons total do you have here? 18. How many protons do you have? So you have plus 17, right? I'm gonna repeat. In the form of questions. Does everybody agree that chlorine has 17 protons?
Yes.
Does everybody agree that before becoming an ion, it has 17 electrons as well?
Yes.
Does everybody agree that chlorine atom doesn't have a charge? It's electrically neutral because 17 pluses and 17 minuses cancel each other out.
That's what I got.
Now we add 1 extra electron. How many protons do we have? Still 17. So that's your protons. But how many electrons do we have right now? Okay? 17 minus 18 minus 1. The sign is super important. Minus 1. So this whole thing has a charge of minus 1.
Did we say -1 or -1?
Negative. Well, if you would say minus 1, it's fine.
Okay.
But
I'm already confused.
we can say minus 1, we can say -1.
Okay.
Okay? Before we move any further in our conversations, does that make sense? Yes? Okay.
But then when you write it,
So again? So again?
So when you rewrite it, you will write it the CL -1 or -1.
How about this? We're going to do the full sort of explanation on the side, okay? We're going to take examples that are not in the notes, and you will guide me through, okay? Sounds fair? So what we're going to try is let's start with a sort of simple stuff, which will be potassium bromide. Okay? Actually, no. We're going to do potassium chloride. Okay? So we're going to start with the potassium. The number, atomic.
19.
The mass, 39. Protons, neutrons, electrons. So far, no questions? Here's your nucleus. How many layers? Why? Because it's a 4th period. 4 layers, right. How many electrons? Remember, only outer one is, the valence, right? So since potassium is in the group 1, how many electrons does it have on the outer shell? 1. The number of the group is 1. It means 1 electron on the outer shell. That's the outer shell. Okay.
And then it's the period. Okay.
Outer. Okay, makes sense so far? Do you follow? Okay. So, how many electrons, if you start looking at noble gases, how many electrons, remember, what is the closest noble gas to potassium? Argon. So, the rest of the atom you can fill using argon. So how many electrons in the first shell? You see those three numbers to the right of argon? Yes. How many electrons in the second?
8,
Third?
8.
Does it check out? Yes?
Yes.
2, 8, 8, 1. So 19, right?
Oh, okay.
19 electrons. Okay? Good? So, okay. Now, what we decided? Chlorine, yes. So now we have chlorine. Number? Mass? Protons? 17. Neutrons? Electrons? I'm going to make them face each other, okay? Number of shells for chlorine? 3. Why? Period 3. So these are outer shells. Chlorine, which group is it in? 17. Everybody agrees? 17. So how many electrons on the outer shell then? 7. For group numbers 13, 15, and so on, you subtract 10. Okay? Let me make a little table here. Remember, first of all, it's all recorded. So, we're talking 1, 2. I'll come back to this. 13, 14, 15, 16, 17, 18, right? So we go 1, 2, 3, 4, 5, 6, 7, and 8. Good? Fantastic. All right. Now, since now you know how many electrons on the outer shell then? 7. How many electrons on the first shell? Second? Checks out? Cool. So now we're going to do, so again, 17 electrons. Now we're going to do a transfer. What's easier? To strip 1 electron from potassium? Yeah, right? Let's do it. Okay? So, as the result of this process, potassium loses 1 electron. What charge does it have now? Say again? Plus 1. Think of it this way. Losing something negative is the same that getting something positive. When you lose an electron, when an atom loses an electron, it becomes 1 positive. Does that make sense? So potassium has a charge of plus. Is that clear? So I'm going to highlight it here. So we have 19 protons and 18 electrons now. Okay? Does that make sense? Let me actually remove it. Okay. Before we move on, does that make sense? Okay, good? Okay. Chlorine will get this electron. It was 7, now it is 8. So it will be 1, but not plus. Minus. Because it still has 17 protons, but 18 electrons now. Am I making sense? Now, look at the structure of 3 shells. Potassium has 288, and chlorine has 288. Can you see that? Take a look at the periodic table. Look at argon. 288, that's what the noble gas is. They both have the same configuration of electrons as a noble gas, which means they're super stable. Does that make sense? Sounds good? The whole concept. Okay. Any questions before we move on? Okay. This is naming. In my opinion, like this, the stuff that we discussed, that stuff, is understandable. There is a logic. This is naming, there's rules. I don't find it particularly exciting. So, how do you name ions of metals? You just keep the name of a metal. Sodium ion, potassium ion, aluminum ion. Does that make sense? Nothing changes. How do you form the names of ions for nonmetals? First syllable plus IDE. Okay? Let me show you. Basically, okay. Let's say we have nitrogen. First syllable. N-I-T-R. T-R. Okay? Nitride. We have chlorine, chloride. Understood? And you just keep going and going and going. Okay? So, this is relatively simple. You should know that. Okay? Charges, those are pretty standard. So as we discussed, first group loses 1 electron, becomes 1 positive. Second group loses 2 electrons, becomes 2 positive. And the only member of the group 13 that we're going to be using is aluminum. So 3 positive. Are we good? For nonmetals, so if you think about this, if an atom has 7 electrons, okay, it needs 1 to achieve 8 octet, so 1 negative. If the atom has 6 electrons, like oxygen or sulfur, they need 2, so 2 negative. And if it has 5, it needs 3, so 3 negative. Okay? Make sense? I'm going to skip it. Just, I don't want to waste time on this crap. Like, yes, there are ions. Okay? Right. So now we're going to learn how to write the formula for ionic compounds. First of all, you will see the examples. First of all, properties, obviously, consist of positive and negative ions. Right? Usually have high melting points and solid at room temperature. Can you give me an example of the ionic compound that you use every day?
H2O.
No, that's not ionic. Go on. No? Kitchen. Salt. Ionic compound. Sodium chloride. No. Covalent. Huh? No. It's solution of chlorine. Sodium chloride is ionic compound. Question.
I forget, how do we tell the difference between an ionic versus a covalent bond?
May I re-ask the question, and you will tell me if that's what you're asking, okay? How do we know the difference between ionic compound and covalent or molecular compound? Ionic compounds are always formed between the metal and non-metal.
Oh, right.
That's it. Okay, covalent are always non-metal and non-metal. Does that make sense, folks? Okay. So I can give you some more examples. Epsom salt, magnesium sulfate, that's ionic compound. The salt that you use for ice, whatever, ice melting thing, it's calcium chloride. Okay? So there are ionic compounds that you use in your day-to-day life. Okay? They are solid at room temperature, and they do have high melting points. Good luck melting salt. Okay? The bonds that, the reason why they are solid and the reason why they're so hard to melt is because individual ions are held together by ionic bonds, which are pretty strong. So we used sodium chloride as an example of ionic compound. Okay? You can actually do the very expensive atomic force microscopy to see that the salt, sodium chloride, consists of ions of sodium and ions of chloride that are organized as a lattice. Does that make sense? I think we have a better illustration. Okay. Before we move on, I want to highlight. So you have to understand, every ionic compound consists of positive ions. We call them cation, and negative ions that are anion. Okay? This is terminology. So when we look at the formulas of a compound, so formula of sodium chloride is NaCl. Okay? We always write the lowest whole number ratio. Let me illustrate that statement. Do you agree that the number of, so like if you take a crystal of salt, it's going to have the same number of positively charged sodium ions as the number of negatively charged chloride ions? It will. Because if it's not, then it's going to be charged. Does that make sense? If you have one sodium and two chlorides, it's negatively charged. It has to. Salt is not charged. It's electrically neutral. Okay, make sense? So, can I say this, or this, or this? Technically, yes, but we never do that. Because the lowest ratio is 1 to 1. Does that make sense? And here's something I want to emphasize. Let's just read the formula. This formula tells you that in salt, one sodium cation per 1 chloride anion. This is what the formula tells you, that the ratio is 1 to 1. Does that make sense to you all? Good? So, a different example, I will get to, different example would be magnesium chloride. This formula tells you that this compound has 2 chloride anions per 1 magnesium cation. Okay? This is how to read the formulas. The last example that I want to make, we have 4, 7, 10, total of 15 people in this room. One person just left for the restroom, but 15 people, right? Including me. How many males do we have? 3, right? So we can say that if we consider this group a formula, a compound, quote unquote, so we can write down this. We have 12 females, right? And 3 males. Does everybody agree with me? So the formula that we can write will be females 12, males 3. This is the formula of our class. Subscripts show the ratio within the compound. Please remember that. Does that make sense to you? Yes, no, maybe?
Maybe. Repeat it.
I'm going to throw a curveball. So this formula of aluminum oxide, what does it tell you? It tells you that for every 2 ions of aluminum, there are 3 ions of oxygen. Well, oxide ions. Does that make sense? This is how you read the formulas. It applies to any compound, not just ionic. For instance, if you look at the simple compound carbon dioxide, it says that per each carbon, there are 2 oxygens. Does that make sense? So this is an example that I just gave you. Magnesium chloride. Now, this actually provides us with sort of a way to peek into how we write those formulas. Because compounds, whether they are ionic or covalent, have to be electrically neutral. Am I making sense? Good? Electrically neutral. So, magnesium, which group does it belong to? No. Group. The vertical is a group. 2. Group 2. Means 2 electrons on the outer shell. Chlorine, on the other hand, belongs to group 17. So 7 electrons on the outer shell. So magnesium will lose 2 electrons. 1 electron will go to 1 chlorine. Another electron will go to another chlorine. Does that make sense? So 1 magnesium makes 2 chlorines happy. Do you agree with me? So when magnesium loses 2 electrons, now it has 2 pluses as charge. When each chlorine gains 1 electron, each chlorine has 1 negative charge. Okay? What is the total charge between 2 chlorines? -1, -1, -2. Does that make sense? Yes? Okay. So magnesium 2 plus, 2 sodiums give total of 2 minus. They balanced out. So this is the rule for you. Total positive charge must match total negative charge. So here's another example. There will be some learning check, okay? Here's another example. Sodium, which group is it in? 1. So 1 electron. Sulfur, which group? 16, so 6 electrons. Right? So in order to be quote-unquote happy, each sodium should lose 1 electron, and each sulfur should gain 2. So we need 2 sodiums to make 1 sulfur happy. Okay? When each sodium loses an electron, 2 of them give you the charge of 2 plus. When sulfur gains 2 electrons, 2 minus. Don't worry, we're going to do some practice. So the first practice that we're going to do is barium and chloride. Okay? You already have a charge. I'm going to ask something else though. Why does barium have a charge of 2 plus? Because is what? Loses 2 electrons. Why does it lose 2 electrons?
Because of there were just 2 electrons in the outer shell.
Why are there 2 electrons on the outer shell only in barium? Because it's group 2. Does that make sense, the whole logic?
Yeah.
Want to do it again?
Yeah.
Which group is barium in? Number 56.
Is in group 2.
How many electrons on the outer shell then? 2. So how many electrons can it lose? 2. And if it loses 2, it becomes 2 plus.
Okay.
Chlorine, which group is it in? 17. How many electrons on the outer shell? 7. Minus 10. 7. How many electrons are needed to 8? 1 more. In order to get from 7 to 8, you need 1 electron. So chlorine will get the charge of -1. Now, look. Barium, chlorine. The charge of barium is 2 plus. The charge of chlorine is minus. How many chlorines do you need to balance 2 positives out? It's a formula. Okay. Now, we're going to go with aluminum. So first is aluminum, and second is bromine. Okay? Which group is aluminum in? 13. So how many electrons on the outer shell? Is it going to lose or gain? At 3, still losing. So if aluminum loses 3 electrons, how many does it have? My bad. This is not what I was going to say. Let me say it again. When aluminum loses 3 electrons, what charge does it have? Positive. Positive, because you lose negative. It's the same as becoming positive. Does that make sense? Okay. So, it becomes positive. How many positive charges if it lost 3 electrons? 3. Bromine, which group? Br, 35. 17. So, how many electrons? 7. How many does it need to become happy? Just 1. When bromine acquires, before we move on, does that make sense? When bromine acquires an electron, what charge does it gain? Negative, how many? Just one. How many bromines do we need to offset 3 pluses in aluminum? That's your aluminum bromide. Okay? You will have to recognize. You don't need to, it's all multiple choice. But you do need to, like, what is the formula for blah, blah, blah? And you have to recognize. Now, let's do this. And I'm going to, well, it does have a curveball. Okay? So, correct formula for this godforsaken combination. I will explain why it's godforsaken. Sodium, what's the charge? How many? 1 plus. Oxygen, what's the charge? How many sodiums do you need to offset 2 minuses? Make sense? Why I said godforsaken? This compound does not exist. Sodium is so reactive, it explodes if you throw it in the water, for example. It burns it, like it produces flames in air. Like it's not, it doesn't exist. Just FYI, okay. Aluminum and chloride, we just did that. What will be the answer? Very similar.
1.
Yes. That makes sense? Bromine was the same, just good? How many charges on aluminum? 3 of what sign? 3 plus. How many charges on chlorine? 1 minus. In order for them to cancel each other out, how many negative charges do we need?
So the only thing I'm confused about is why is the answer for, like, why is it written differently for both answers?
I'm not sure what you're asking.
So you know how that one is Na2, then it's...
Because we need 2 sodiums. Look. How do you do that? You need to put 2 here, right? So it means you need 2 sodiums. Does that make sense?
Yes. Okay.
And this is the curveball. I want you to suggest. Okay, you say that it's number 3? Can you explain why?
Because the sign reverse 3 and 2.
Okay, so magnesium, how many charges does it have?
Positive 2.
Nitrogen, how many charges does it have? Right? So you need to make sure that the numbers, not the signs, the numbers on both sides are the same. What do you need to multiply? What is the, I don't know the mathematical term, the lowest common whatever. No, it's not denominator, it's something else. Yeah, common multiple, yes. What's the lowest common multiple? That make sense? What do you need to do with 2 to get to 6? Agreed? So I have 6 positive total. What do you need to do with 3 to get to 6? Multiply by 2. So I have 6 negative charges total. 6 positive and 6 negative charges. Do they work? Do they cancel each other out? Yeah.
So how do you do this with 3?
Wait a minute.
Like 3 elements?
Good question. First, the ionic compounds that we are talking about right now will be always binary, like 2 elements, that's it. We will get to what's called like compound ions or complex ions. We'll figure it out then. Okay? Right now, 2 elements. Does that make sense, folks? Any questions? So, okay, naming and writing, that's pretty straightforward. We talked about it, this. So you take the name of the metal is the same, and then the name of non-metal, but you change it to like chlorine to chloride, bromine to bromide. All right? So this, what is that? Okay, potassium. Remember, metal always goes first. What is that? Oxygen. This is your first syllable. You add the ending ID. Right? Let's just practice. Hold on. What is the first symbol? Li. Lithium. What is S? Sulfur. Let's do the transition. That's the first syllable. Do you agree with me? What do you need to add? Which ending? IDE. Sulfide. Okay? What is the first element? What is the second element? It's your first syllable. Finish it. Nitride. Does that make sense? Okay. Formulas. Go on, the first square right here. What should I write in terms of the formula? Okay, it's going to be this. Do I need any subscripts? No? Why? That's the right answer. Because sodium is one positive and bromine is one negative, right? What's the name? Sodium. Bromide. Next square. Do I need subscripts? To where? At sodium. Does that make sense? What is the charge on sodium? 1 plus. The charge on sulfur? 2 minus. So you need 2 sodiums. Does that make sense? No? Okay. What is the charge on sodium? How many? It's right there on the slide. 1. What is the charge on sulfur? Minus. Yes. So, in order to match 2 minuses, how many pluses do you need? 1 plus, 2 minus are not equivalent. How many pluses do you need to compensate for all minuses?
2.
There you go. Does that make sense? So you need 2 sodiums. Means you put subscript after sodium. Okay? What is the name? Well, obviously sodium. Sulfide. What's the formula here? Na3N. Because nitrogen has a charge of -3 and sodium has a charge of +1. So you need 3 positively charged sodium ions to offset 3 negative charges from a single nitrogen. Does that make sense? What is the name? Nitride. Go on.
We write nitrate.
Don't. This is the solid rule. We'll get there when we'll get there. We will do that. Okay. Good. Can we just do the formulas, huh? Because the name is going to be aluminum, and then you already have the anions. Like it's the same. Formula for aluminum bromide. Al. Okay, we need to solve that. You think Al3? If you yes, AlBr3. Because how many positive charges do you have in aluminum? 3. How many negative charges? 1. So, how many negatively charged bromide anions do you need to compensate for 3 positive charges on aluminum? You need 3 negative bromides to compensate for 3 positive charges coming from a single aluminum. What about this? Aluminum sulfide. So I'm going to show you sort of how you can do that. Actually, how many positive charges one aluminum has? How many? Let me just start it over because, okay, in the center. Aluminum sulfide. So how many positive charges from the aluminum? How many negative charges from sulfur? So what is the... So you cannot use fractions, right? Otherwise you would like add 1.5 to sulfur. Okay? You can't do that. But you need to come to some number that will be common. So which will be 6 and 6. How do you get there? 2 aluminums and 3 sulfurs. Does that approach make sense? So if the charge, so positive and negative charges in terms of the numbers must match. And that brings us to this. Do I need to do anything here? Because the charge in aluminum is what? 3 plus, and in nitrogen, 3 minus. Does that make sense? That's it. They match. It's all good. Okay? Okay. So I understand that like your head is boiling. Let's take a pause. I'm gonna save it. And if we, so let me just do this. So I hope now that that kind of started making sense. And now we're going to talk about the transitional metals, metals with the variable charges. So when we were talking about ionic compounds before, we only wrote down the formulas for the compounds that are formed by metals from the group 1, group 2, and aluminum. Because those guys always have the corresponding charges. So group 1 1 plus, right? Group 2 2 plus. Aluminum 3 plus. Well, most metals that we're going to be dealing with can have different charges. For instance, copper in some compounds have a charge of plus 2, and another is plus 1. Iron has two very distinct, chemically distinct forms. Ferrous iron with a charge 2 plus, and ferric iron with a charge 3 plus. Not going to read you the examples, but the way you name the compound is that you need to specify what charge a transition metal has in your compound, and when you write the name, you have to put the charge, and its positive charge obviously, in the form of a Roman numeral. Let me give you an example right away. Okay? So copper 2 chloride. Does that make sense? Now, here's another example. For instance, I tell you that the compound that we have is iron sulfide. Okay? We mentioned multiple times that sulfur, the nonmetal, which is located in the group 16, has 6 electrons on the outer shell. Right. In order to get to octet, it has to collect 2 electrons, right? Yes? So sulfur is going to get the charge of 2 minus. This is the actual formula of iron sulfide. So how many irons in this formula are per 1 sulfur? What is the ratio between the iron and the sulfur? Don't look at the table. Look at the slide. 1:1, right? 1 iron per 1 sulfur. So this is an actual formula, right? So if the charge of the sulfur is -2, the charge of iron has to be +2 to get them balanced. So the name will be iron, then you specify the charge 2 sulfide. Okay? Again, the number of ions that transitional metals can form is insane. They are not, it's actually not an exhaustive list here. Okay, those are common ions. Wait, what? Okay, I don't know, something was happening. Okay, that's not an exhaustive list. But we will try to determine the charge based on the formula, just like we did before. So here's an example. Manganese fluoride. Fluorine, which group is it in? 17. How many electrons on the outer shell? 7. How many electrons does it need to get to 8? 1. So if it gets 1 electron, what is the charge on the fluorine? -1. How many fluorines do we have? No. How many fluorines do we have in the formula? 2. So we have 2 of negatively charged fluorines. So how many negative charges do we have in total? Agreed? We have a total of 2 negative charges. How many positive charges do we need to compensate? Also 2 positive charges, right? These 2 positive charges have to go onto manganese, which means in that situation, manganese has 2 positive charges, and fluorines each has 1 negative, but there are 2 of them. So, since it's a transitional metal, manganese to fluoride. Does that make sense? So now to make it, I don't know who came up with the idea to put all those things on the periodic table. Here's what I want you to understand. Listen to me. For metals and for hydrogen, the charges are always like this. Magnesium will always have a charge of 2. In other words, I don't know how to emphasize it more. Elements of the first group, if they become an ion, they have a charge of 1+. Members of the second group, including beryllium, have a charge of 2+. Aluminum has a charge of 3+. Okay? And if we talk about, do you understand the term binary compound? Two different elements. So these guys, the ones that I just highlighted here, these ones, always in binary ionic compounds. I want to highlight ionic. So if it's together with a metal, if there is one metal and one chlorine, do you follow my train of thought? Metal and chlorine. Chlorine will always have a charge of -1. Sulfur is always going to have the charge of -2. Okay? Good. Please don't even think about memorizing this crap. I will never ask you what are 2 possible charges for copper. I don't really care. Am I making sense? Or what are 2 common charges for cobalt? So now let's name the compounds, okay? So what is the charge of chlorine in the binary ionic compounds? How many electrons does it have? Huh? To get, wait, chlorine, which group? 17, subtract 10. 7. How many do you need to get to 8? So, -1. How many chlorines do you have in that formula? 2. What is the total number of negative charges? So total number of negative charges is 2. Clear? How many positive charges do you need to impose on iron? So the name will be iron. What should I put in parentheses? Roman numeral 2. Does that make sense? Couple more? Yeah? Let me think. All right. nickel sulfide. We need to add the numeral. Sulfur. What charge does it have? Always in, -2. Everybody understands why -2? Which group is it in? Let me write this thing down. How about that? It will be on the recording and you can get back to it anytime. So listen. Sulfur. Group 16. So how many valence electrons? 6. To get to 8, how many does it need? So it gains 2 electrons to get to 8. Charge, if it gains 2 electrons, will be -2. How many sulfurs do we have? Each of them is 2 negative. So total negative charges is what? Let me say it again. How many sulfurs do we have? 3. Each sulfur has what charge? -2. So that gives us 6 negative charges. How many positive charges should nickels have? 6 positive charges. How many nickels do we have in this formula? So if we have 2 nickels, and that gives us 6 positive charges, how many positive charges does each nickel carry? 3. Does that make sense?
Yeah.
So we have 6 positives because we have 2 nickels. Each of them is charged positively, 3 positive. And we have 6 negatives because we have 3 sulfurs and each carries 2 negative charges. Okay, this is sort of an extreme example. What should be the name? Nickel. No. What is the charge on each individual nickel? So nickel 3 sulfide. Okay? One more. That's going to be simple. Hang on a second. Go on. Say it again.
Like we started with the sulfur. You always start at the last element of the problem.
I'm not sure I understand the question. When we start naming, that's what you're saying?
Yes,
We always start with the metal.
that's right.
That's it. That's it. So, real simple example. Copper. What is the charge on the chloride anion? Plus -1. Because remember, those guys, non-metals, they gain electrons, right? So -1. What is the charge on copper then? Positive. How many? 1. Does that make sense? Chloride is -1. Copper is +1. They cancel each other out. So, what's going to be the name? Copper 1 chloride. To make it super clear, if you have a question, something like, name this compound, okay? If you select the answer that says cobalt chloride, it is incorrect. The correct answer is cobalt 2 chloride. This is super important because it's a language. Okay? Right? So you can do the opposite. Based on the name, you can write a formula. So look at this. The name is iron 2 chloride. What does that mean? It means that the iron carries 2 positive charges because of that number 2. Okay? Chlorine, chloride ion, carries how many negative charges? Each ion. Okay, I need to correct myself here. Listen, folks. When I say chloride ion, I mean each individual ion. So -1. Does that make sense? So iron 2 plus, chloride 1 minus. But how many chlorides do we have? So we have 2 pluses, and we have 2 ions, each of them 1 minus. So they compensate. Okay? Now, I want you to find in this table three mistakes. Say again?
Copper and phosphide.
Why? Phosphorus, which group is that? Phosphorus, which group? 15, right? The column. 15. So how many electrons on the outer shell? 5.
Or 5 because we have the
Minus 10. Minus 10. 5. How many electrons needed to get to 8? 3. So phosphide will have the charge of 3 minus. Copper, since it says copper 1, a charge of 1 plus. How many coppers do we have? 3. So we have 3 positive charges, and we have 3 negative charges. That's all good. What about the next one? What is the charge on chromium? Well, it says 1. So, how many chromiums do we have? Also 1, right? In the formula, there's no subscript, right? What is the charge on bromide? 17th group. -1 to get from 7 to 8. How many bromides do we have in the formula? Positive and negative, do they cancel each other out? No. No. I'm very happy to say, I did not prepare this table. Okay? So, it's a mistake. There could be 2 ways. Well, first of all, for chromium, having like one charge, super rare. Most likely what they were trying to do is this. Chromium 2 bromide. Then it would work. Make sense to you? Same story with tin. But the most egregious mistake is with lead, Pb. Sulfur. Which group does it belong to? 16. So how many electrons on the outer shell? 6. 6. How many electrons are needed to get to the magic 8? 2. So we have 2 minuses. For God's sakes. 2 minuses, right? How many sulfurs do we have? So how many total negative charges do we have? 4. How many leads do we have in the formula? Just 1. So this lead has to carry 4, not 1 charge. Does that make sense? So the name should be lead 4 sulfide. Does that make sense? So these 3 are errors, mistakes. Okay? Good? So let's do the practice here. Tin 2 chloride. I'm sorry. So tin chloride. Now we need to figure out subscripts, right? Correct? What is the charge on chlorine? -1. According to the name, what is the charge on tin? Two plus. Make sense? How many chlorides do you need to offset 2 positives? It's your formula. Make sense? Okay, so we're going to wrap up right here because polyatomic ions is a huge chunk. Okay. So just a reminder that last week we talked about how to write names for fairly simple ionic compounds. And we mentioned that if you are, just a reminder, if you are dealing with the ionic compounds that are formed by the metals from the first and second groups of periodic table and aluminum, all you need to do is to say the name of the metal, say potassium, and then whatever anion you have there, like potassium sulfide. If you're dealing with transition metals, which are other metals, then you need to highlight the valency, how many electrons are taken off that transition metal, like we have here, tin 2 chloride. Okay. Now we're going to talk about polyatomic ions. So I'm going to spend some time explaining the concept because students sometimes get confused about the presence of multiple elements in a single ion. So what is a polyatomic ion? When you think about the ionic compound such as potassium iodide, you effectively can imagine that as the potassium ion and the iodide ion. Makes sense, right? But if you're talking about a polyatomic ion, for example, the compound that was shown on the previous page here, aluminum hydroxide, this OH group acts as a single ion. In other words, we can imagine that this way. So aluminum with the charge 3+, right? Makes sense? And 3 ions, each of them containing oxygen and hydrogen. And overall charge on the OH is 1-. So you don't treat individual atoms, individual elements within the polyatomic anion or cation. You don't treat them separately. You treat them like they are the entire entity. Does that make sense? When we will talk about it, I will give you more and more illustration of that. So the only polyatomic cation that we're going to mention is the ammonium. Everything else that is polyatomic is going to have a negative charge. So these are 2 examples of salts that consist of polyatomic ions. So first is calcium sulfate. So the positive ion in calcium sulfate is, well, calcium. This is the entire ion, SO4. And this entire structure has a charge of 2-. It's not oxygen, it's not sulfur, it's all of them together have a charge of 2-. Clear? Now, this is the ammonium nitrate, which serves as the fertilizer. So here you can see the ammonium cation. The blue atom is nitrogen. The white atom is hydrogen, so you have 1 nitrogen, 4 hydrogens, right? And when they are combined together, the total charge of that ion is 1+. Here is also a nitrogen atom covalently connected to 3 oxygen atoms. Altogether, this entire particle has a charge of -1. Sounds good? So I will explain the logic behind the names of polyatomic ions and why we call them a certain way. Okay? So, generally speaking, if you have the ending ATE, the ion has more oxygen atoms than the one with the ending ITE. Do you see that? Nitrate, how many oxygens? 3. Nitrite, how many oxygens? 2. Chlorate, how many oxygens? 3. Chloride, 2 oxygens. Now, chlorine is kind of weird because it forms 4 different polyatomic ions. And in order to specify, this, we add perchlorate, like extra chlorate. And in order to specify when you have just one oxygen, we add hypo. To be fair, you're not going to run into these compounds very often. Okay? So, the best way to learn the names is to use them. I'm going to check at the end of this chapter when we finish talking. I think the handout for the exam has the names of polyatomic anions. So you don't have to brutally memorize that stuff, okay? Now, here's another example. For instance, here, sulfate 8, right? It has 4 oxygens. Sulfite has 3. Okay? Phosphate has 4 oxygens. Phosphite has 3. Does that logic more or less? Does it make sense? Okay. Couple of additions. Sometimes polyatomic anions may contain variable number of hydrogen atoms. For example, here. So if you look at phosphate, sometimes in addition to PO4, there is a hydrogen. If there is one hydrogen, we call it hydrogen phosphate. If there are 2 hydrogens, dihydrogen phosphate. Okay? Sounds good? So now we're going to write a formula for aluminum bicarbonate. The chemical symbol for aluminum is Al. Is it clear for everybody? So we can write Al. Can you take a look at the periodic table and tell me, first of all, in which group aluminum is? 13. And how many electrons aluminum as a metal is going to lose? Do you remember? 3. 3, right? Because when we have this double-digit numbers of groups, we subtract 10. Okay? Good? So it's going to lose 3 electrons, which means it's going to have a charge of 3+. Agreed? Everybody? Okay. Now we need to figure out the formula for bicarbonate. I mean, I know it, but here, bicarbonate. HCO3, and the charge of that entire thing is 1 minus. Can you all see that on the screen? Okay. So we're going to write down HCO3 with a charge 1 minus. Now remember, this salt, this compound, has to be electrically neutral. So if aluminum provides 3 positive charges and a single bicarbonate anion provides only 1 negative charge, how many bicarbonate anions do you need to balance 3 positive charges? 3, yes. So 1 aluminum and 3 bicarbonates. So the common confusion is, like, what is the difference between these 2 subscripts, right? Let me explain. The first subscript here, it shows you that bicarbonate anion contains 3 oxygens. That's it. Once you put brackets around it, that second subscript shows you that there are 3 ions that are contained within the brackets. Clear? So we're going to practice, for instance, sodium phosphate. So I'm not going to scroll back to the table if you don't mind, because I kind of know the formula for the phosphate, but tell me please, sodium, Na, what charge is it gonna bear? Huh? +1, exactly. Now phosphate has 3 negative charges. So obviously you don't need extra phosphates, but you do need extra sodiums, right? So how many sodiums do you need? 3, exactly. So the formula will be Na3PO4. Now, when you are dealing with a monoatomic ion, like sodium, chloride, you don't need to put them in the brackets, right? But once you start dealing with polyatomic, if there are several of them, you have to put them in the brackets. I'm going to give you an example. So, what if we need to write a formula for ammonium phosphate? Ammonium is the only polyatomic cation that we're going to be dealing with. So in order to balance 3 negative charges that phosphate provides, how many ammonium ions do you need? 3, yes. So you write down NH4. What should I do next? Since I need 3 of them, I should put brackets. What should I write down? 3 subscript, yes, and PO4. Does that make sense? Good? Okay. So naming follows pretty much the same rules as with monoatomic anions. First, you write down the metal or ammonium, and then polyatomic anion. Okay? If we are dealing with metals from the first and second group and aluminum, do we need to put these Roman numerals after the name of the metal? Taylor? No, we don't. So, sodium sulfate. But when we are dealing with transition metals, like iron, then we have to put the number after the metal. So let's figure it out. First one, what is this metal? Calcium. Now this has to be something with nitrogen, right? And since it's the top line, so to say, like it cannot contain any more oxygens, like it's the top 3 oxygens is the max, it's going to be nitrate. Okay? This is tin. The Latin name is stannum. This is why it's SN. Okay? Now, this is actually a really good example. So, we have tin and we have sulfate anion, right? I can tell you right away that the charge on the sulfate anion is 2-. In this formula, which is correct, how many sulfate anions do we have? It's not a complicated question, folks. 1. No. 1. We have 1 anion because SO4 is a single anion. Clear? How many tin cations do we have? 1, yeah. So, if we have 1 sulfate with a charge 2-, what's going to be the charge on the tin cation. So plus. So we have to say tin, 2, sulfate. Make sense? Okay. Few more practice examples? Yes? Okay. Let's try to focus on something that you can find in the household. So, let's figure out the way to name baking soda. What is the cation? Positively charged ion. Which one is positively charged here? Sodium. Which one is negatively charged? The anion, right? This thing. You could tell me HCO3, I would take that answer, folks. HCO3 is the single anion. Make sense? Which is charged 1 negative. And it is called bicarbonate, or alternatively hydrogen carbonate. Nobody calls it that. Okay. You're familiar with Epsom salt. Now I'm going to give you a name. It's magnesium sulfate. Okay? Good? So, magnesium is this. Sulfate is this. Question number 1. What will be the charge on magnesium? Thank you. And I'm telling you that the charge on the sulfate is 2 minus. Do I need to add any subscripts? Fantastic. Absolutely not. Now we're going to add, I think there is magnesium phosphate in like Tums, whatever. Let's do magnesium phosphate. Just, nothing complicated. So this is your magnesium. The charge is 2 plus. This is the phosphate. The charge is 3 minus. This is the curveball. What do you need to do? Remember, you cannot use fractions as subscripts. So it has to be a whole number. We did similar thing last week. No, what you have to make sure that the number of positive charges and the number of, say again? The 6, yes. So how do you get 6 positive charges? How many magnesiums do you need to reach 3 magnesiums? And how many phosphates do you need to reach 6? 2. That's your formula. Okay? Does that make sense, everybody? Good? And the last practice. Sure, go ahead.
So this is further up. So the SN, the 10.
Yeah.
Where's that at on
Periodic table, number 15.
group 2?
Oh, it's group 14. It's transition metal. You see, it's not in a group 2. This is why, hear me out. This is why we put that little 2. Because it is a transition metal. Okay? I'm going to give you I'm going to try to compile all challenges into one structure. Okay? One salt. And it's going to be iron 3 sulfate. Okay? So what does this number mean? The number 3, what does it mean? What is the charge on the iron then? Positive. How many? 3, yes. This is sulfate. The charge in it is -2. What should be the subscript at iron? 2. What should I do with sulfate? First, put it inside of what? Brackets. And then put 3 over here. And that's your iron 3 sulfate. Does that make sense to you? Yes? You just did. You literally did this for me, which is, we just switched the charges. You literally just dictated me what should I do. Yeah. So this is not exactly, but it is the same concept. Okay? The purpose of this number is to tell you what charge we have on the transition metal. Because for metals from the group 1, group 2, and for aluminum, we already know the charges. Does that make sense? Good? Okay. Now, molecular compounds. The difference between molecular compounds and ionic compounds is that in ionic compounds, electrons, for our intents and purposes, electrons are stripped from the metal and are given to non-metal. In molecular compounds, electrons are shared. Okay? Sounds good? Now, the names are formed in a slightly different way with the quantitative prefixes. So before we start talking about naming them, we need to figure out the difference between ionic bond and the covalent bond. I'm going to provide you with an example, just to remind you what ionic bond is, using the simplest example of sodium chloride, right? So we have sodium and we have chlorine atoms. Okay? How many electrons on the outer shell does sodium have? Just 1. How many electrons on the outer shell does chlorine have? 7. What is the magic number? 8. So sodium is going to lose 1 electron. Okay? And chlorine is going to accept 1 electron. Agreed? Fantastic. When sodium loses 1 electron, what charge does it acquire? Positive 1. So that's your ion, right? And chlorine becomes -1. And the force of attraction between the positive charge and the negative charge is what constitutes the ionic bond. In case of covalent bonds, electrons are shared. So covalent bonds are formed between nonmetals. I always compare, covalent bonds to ionic bonds. Imagine that, I have a brother who's, I don't know, brother, let's say we look at 2 brothers. I do have a brother, but that's a long story, and we're old and we don't play video games anymore. But let's say we have 2 brothers, and one is 16 and another is 4. And they get Xbox, and the 16-year-old says, "Tough luck, dude. You're not going to get any playing time because I can beat you up," right? That's ionic bond. The 16-year-old just takes Xbox, and that's it, right? Now you have 2 brothers that are closer to each other, say 12 and 10. 12-year-old can kind of beat the shit out of 10-year-old, but will face some recourse. So they decide, okay, how about that? We're going to share it. I'm going to use it 4 days a week, and you, 10-year-old, can use it 3 days a week. Kind of fair. Make sense? So that's a covalent bond, sharing. So when we name covalent compounds which share electrons, we use prefixes. You need to know first 10. They kind of make sense. So we usually don't use mono. Okay, so we use di, tri, tetra, penta, hexa, hepta, and it makes sense. So tri makes sense, right? Tetra, it's 4, okay? Pentagon, penta, 5 corners, okay? And so on and so forth, okay? So the first nonmetal in the formula carries its name as an element. The second nonmetal is named using the first syllable with an addition of IDE, very similar to monoatomic anions. So, two simplest examples. Water. What is the first nonmetal? Louder, huh? Hydrogen. Do we need to add a prefix? How many hydrogens? 2. So we need dihydrogen. Okay? What is the second? Okay. But, I think I misspelled oxygen, but it's okay. We leave the first syllable, add "ide." Can you add monoxide? You can, but you don't have to. Sort of by default, we don't use mono when there's one. Okay? When there is no prefix, it means one. Okay? Another example. You know what it is? So first element. Second, so oxide. We call this compound carbon monoxide, but technically speaking, we can say just carbon oxide. But this compound, what do we call it? There you go, carbon dioxide. Right? So, nonmetals can form different types of compounds. This is why we need this prefixes. Okay. Small detail. This does not exist. It doesn't. It just doesn't. Nitrogen cannot do that. I can give you a list of compounds that nitrogen can form when it interacts with oxygen. Let's practice and name them all. Okay? First one, how would you name it? Okay, what is the first nonmetal? Do you need the prefix? Which one? This is the laughing gas. N2O is a laughing gas, the one that is used for anesthesia. What would you name this one? Nitrogen oxide. A very important molecule in the regulation of cellular activities in humans. Okay. During the break, I can tell you a fascinating story about this. How would you name this one? Dinitrogen trioxide. Nothing fancy about this one. It's the next one. Yes. So the reason why modern cars have catalytic converters is partially due to that gas. it's very toxic. In catalytic converters, they convert it. What is that? Dinitrogen tetraoxide. Okay, and what is that? Dinitrogen pentaoxide, yes. Good? Okay, so this is an exception because so technically speaking, we don't have to say carbon monoxide. But traditionally, we call it carbon monoxide. Okay, it's more of a common name than the strictly speaking. Yeah, we just named a bunch of stuff here. Yeah, so this, for example, sulfur dioxide, it is used for preservation of the fruits and vegetables, but also this gas will yield so-called sulfites, salt sulfites. Next time you buy wine, if your age allows that, look at the label. It says contains sulfites. Sulfites are preservatives for wine. They benign for humans. Okay. So now you're proficient. So what is the first non-metal? Nitrogen. Nitrogen. Okay, I'm gonna bromide. And what do you need to put in front of it? Yes. Tribromide. Absolutely correct. So what would be the correct name for the first compound? Number 2, silicon tetrachloride. What about compound B? 3, diphosphorus pentoxide. What about number C? Yes, dichlorine heptoxide. That's a really cool compound. At room temperature, it explodes. It's really cool. You can make it by adding perchloric acid to permanganate, I think. Okay. So how do you know if compound, an ionic, or it is a molecular compound? All ionic compounds contain a metal in the formula or name, or an ammonium ion. Okay? So second lab, remember? Second lab when you were doing the different salts and they should decrease the temperature, right? You worked with ammonium chloride. So that is an ionic compound. Okay? Molecular compounds do not contain metals. Period. Okay? What if it's two metals? Complicated. It's complicated. It's neither. If it's two metals, it's neither. It's neither ionic. Most likely, it is not a compound. Most likely, it's a solution of one metal into another. So like brass, which is what, zinc and copper? I think zinc and copper. It's a solution of zinc and copper. Okay? So, first one. Give me the name and tell me if it's ionic or covalent. Sulfur trioxide. Ionic or molecular. Any metals in the formula. You can refer to the periodic table, whatever. Sulfur is on the very right, oxygen is on the very right. Those are non-metals, so molecular. Next one, Ba stands for barium. Very good. Stop. Stop. Hold on a second. Barium. Find it in the periodic table. Where is that? Group 2. Elements of group 2, are they metals or non-metals? They're all metals, which means it's ionic compound, right? And you don't need to add either di or tri or anything, because what is the charge on barium? 2 plus 2, always. So there is no ambiguity. There is no, like, you don't need, you know that barium has a charge of 2 plus. Does that make sense? Good? Barium chloride, absolutely correct. And it's ionic compound. This one, so the NH4 is the polyatomic anion, which is ammonium. The definition, NH4 is ammonium. The charge is always plus 1. So this is one polyatomic ion. This is another. The second one is phosphate. If it contains ammonium, is it ionic or covalent? Ionic. This one. Oh, this is a doozy. Copper. Okay, copper. I can tell you that this is carbonate. Can you find copper on periodic table? Cu. Is that a transitional? Yes, it is. If it's transitional, what do you need to add after copper? Okay. So I can tell you that the charge in the carbonate, this guy, is 2 minus. Right? It's 2 minus. How many carbonates do you have? I'm not asking hard questions, folks. Like, the information is literally on the slide. Just one, right? Just one. Okay. Let's do it again. This is the carbonate. Just one. So the charge is 2 minus. How many coppers do you have? 2. So what charge does each copper have? Because remember, it has to offset 2 negatives. You have 2 coppers. Okay, you want 2 plus? If you have 2 coppers, and each of them has 2 plus, how many total pluses do you have? 4, which is not what you need to offset 2 minus. Does that make sense? Let me explain a different way. I know how I may actually help you out with this. Okay? Hold on. Take a look. Hang on a second. Okay. How many carbonate anions do I have? Excellent. This is literally an anion. Okay? Good? What charge does it bear? Negative. How many negatives? Always numbers. 2 negative charges, right? How many coppers do I have? What should be the charge on each copper? Positive 1. Am I making sense? So if it's a positive 1 and copper is the transition metal, what should I put in the brackets here? 1. Does that make sense now? You feel free to write this on a piece of paper. I'm have scratch paper if you need to. I'm okay with that. Okay?
I guess it was, when I went to the tutor, he said the subscript is like the number of bubbles.
Yeah. That subscript is the number of bubbles.
The charge.
Exactly. Number of bubbles, 2, times the charge in each bubble.
So within 3 of those,
What do you mean 3?
3 of the CO3s.
How do 3? Because this 3 is, it does not refer to CO3, no. We were talking about this, that this subscript shows you how many oxygen atoms are in the ion. We just talked about it. If the carbonate is in the brackets, like if that would be this, then this shows you that I have 3 carbonates, which compounds like this do not exist, but am I making sense?
So you have brackets, you're saying.
If there are brackets, it means more than one polyatomic anion, okay? What's that? We already named it. The bottom one. Just nitrogen? Nitrogen, tetra, oxide. Okay? Now, I have a habit of combining A and O, not combining, but separating A and O. Sometimes that would be tetroxide. Like in the book, it can be written like this. They just lose one vowel. Acceptable. It's my force of habit. Been writing like this for forever.
It's a molecule?
It is. Yeah. Of course. Thank you. Yes, it's a molecular compound because both nitrogen and oxygen are non-metal. This is something you have to memorize. That's it. First 4 elements of group 17, nitrogen, oxygen, and hydrogen. They exist as diatomic molecules. Does that make sense? So when you see the crystals of iodine, it consists of molecules, and each molecule contains 2 iodine atoms. Does that make sense? This room contains 79% nitrogen, the air, I mean. Nitrogen exists as a molecule made out of 2 nitrogen atoms. Does that make sense to you? You must know that. There are 7 of them. First 4 in group 17, hydrogen, nitrogen, oxygen. Okay, now, the way we wrote formulas so far, the way we described molecular compounds so far was just writing a formula for the most part, right? So Lewis structures show you the distribution of electrons in these molecular compounds and the bonds that are formed. So here you can see Lewis structures for fairly simple molecular compounds. I'm going to introduce a couple of concepts here. First of all, the stick like that represents a single bond. The bond consists of 2 electrons that are shared by both atoms. Okay? So let's break down the first molecule, the methane. I want you to take a look at hydrogen. Right there. How many electrons does hydrogen have on its outer shell? Just 1. So this dot represents the electrons. Carbon, how many electrons does it have on outer shell? 4. because it's 14th group. We subtract 10, that's your 4. So far, does that make sense? Okay. So the magic number for carbon is 8, right? It wants to have 8. Clear? For hydrogen, since it's a period 1, elements in the period 1, hydrogen and helium, for them the magic number is 2. So hydrogen wants to add an extra electron. Neither hydrogen nor carbon are in position to strip electrons from one or another. Okay, we're going to discuss the reasons for that later. But right now, how can we make these guys happy? So this is your carbon with 4 electrons, right? We put hydrogen, and they start sharing these 2 electrons. So this hydrogen is happy. This hydrogen is happy. This is happy, and this is happy. Okay? And if you look at carbon, it has 8 electrons. 4 of them are shared with hydrogen, but that doesn't matter. Okay? So I can effectively replace all these pairs with bonds. Does that make sense to you? Okay? Now, the way I drew it was not super conventional, because usually shared, the electron pairs are written not like, I don't know, like this, but rather this. Okay? So not, how to say, like, not along the line. That's it. That's a tradition. It doesn't bear any conceptual importance. Okay? So if 2 atoms share not 1 pair, but 2 pairs of electrons, you get a double bond. Okay? You can have triple bonds. I'm going to give you some examples. So, the example of a compound with a double bond, okay? Okay, let's do this. So the compound is urea. Okay? I'm just going to show you how it works, right? So urea that we excrete with urine, and by the way, if anyone has a sugar-free chewing gum on you, you can, not necessarily right now, you can look at ingredients. Some of them contain carbamide. It fights the acid in your mouth when you chew it. Carbamide and urea are the same things. Okay? It's absolutely benign for humans. Okay? Believe me, it's not extracted from human urine. Don't worry about that. Yeah. So let's talk about this. So we're going to put, you will not have to produce this sort of complicated Lewis structures. I just want to exemplify. A double bond. So carbon, how many electrons does it have on the outer shell? 4. Okay? Hydrogen, how many electrons does it have on the outer shell? 1. I'm going to do the electrons like along, okay? You good? So these 2 hydrogens, are they happy? Yes, I can replace it with an arrow. Those are bonds. Now, how many electrons carbon has now, including shared ones? Actually, change it. No. Okay. 6, right? So it needs 2 more. Clear? Now, oxygen, How many electrons does it have in the outer shell? 6. Okay? So what we're going to do, how many electrons does oxygen need to be happy? 8. 2 more. 2 more. Carbon has 2 unshared electrons, needs 2. Oxygen has 2 unshared electrons, needs 2, right? So what we're going to do, we're going to do this and this with oxygen. So now, how many electrons does carbon have? 8, including 2 shared with hydrogens and 2 shared with oxygen. And oxygen has 8 electrons as well, because it shares 2 electrons with carbon. That make sense? Okay. Triple bond, a little bit more complicated compound. Acetylene. I don't know if you ever worked like in construction or something, when like people cut the sheet metal with like a flame. They use acetylene burner. Acetylene and oxygen produce a very high temperature flame, about 14 degrees Celsius, 1400 degrees Celsius. Okay, so carbon has 4 electrons, right? Each of them has 4 electrons. So we already got 2 shared, right? Hydrogen has 1. It's 2 more. But while both hydrogens are happy, carbons aren't. Do you see that? Because each carbon right now, with all the shared electrons, only has how many? 6. 2 here, 2 here, and 1 and 1. So what they're going to do? They're going to share these electrons. Okay? So these 2 carbons, in my example, share 3 pairs of electrons. So you have 1 bond for a pair, another bond for a pair, another bond for a pair, and a single bond with a hydrogen. Okay? So now we're going to try to explain why some compounds, why some elements form ionic bond and why some elements form covalent bonds, and my analogy with the Xbox will come in handy again. So for this we need to discuss the concept of electronegativity. Okay? So electronegativity is, like, qualitatively a very simple concept. Before we start, I have a question. What is the sign of a charge in the nucleus? Yeah. Nucleus in any atom. Nucleus is positive. Agreed? Charge on electrons, negative. Positive charge and negative charge, what do? Attract. So electronegativity shows you how, quote-unquote, hungry a particular nucleus for electrons. More electronegative elements pull electrons with a greater force. Okay? In my analogy with 2 brothers, the age, the size, the ability to take Xbox is electronegativity. When you have a 16-year-old and a 4-year-old, 16-year-old is much more electronegative because they can just take an Xbox and that's it, end of story. Okay? Now, electronegativity shows a specific pattern of changes in the periodic table. Okay? For this, it would be convenient to just like look at periodic table and reference it in your mind. So when you move from left to right in the period, okay, electronegativity increases. So let me ask you this. Now, I'm going to add a note. Exclude noble gases. So basically, when we talk about reactions and we refer to periodic table, you can forget about noble gases completely. That makes sense. Like, just ignore them. So if you forget about noble gases, period 4, for instance, what is the least electronegative element in the period 4? Potassium. On the very left. What is the most electronegative element in the period 4? Bromine, Br. Does that make sense? Because it steadily increases from left to right. Is that clear? It also increases from the bottom to top. So in the group 17, what is the most electronegative element if it increases from the bottom to top? Fluorine. That makes sense? Now, a little bit trickier. In a group 1, what is the least electronegative element? It increases from bottom to top, which means it decreases from top to bottom. You can say just letters. You're absolutely right. Francium doesn't really, nobody works with it because it's extremely radioactive. It's going to be cesium. Like in real life, it's going to be cesium. Okay? So, does that make sense? Okay. This illustration, okay, makes probably more sense because it's not words, it's an image. So you see how it increases from left to right? We can say that it decreases from right to left. It increases from bottom to top. Or decreases from top to bottom. Before we're not going into why, but does that make sense, the whole rule? Okay? So these numbers are electronegativity units. They're not measured. It's a relative. Okay? Does that make sense? So for instance, I can say that fluorine is 4 times more electronegative than lithium. Clear? Now, do you think you need to memorize these numbers? Absolutely not. I happen to know that fluorine is 4, oxygen is 3.5, and I believe chlorine is 3.5. That's all I know. Yes, no. I was wrong about chlorine, you see? I was wrong. So I effectively remember these 2 guys. That's it. Nobody in their right mind tries to memorize this stuff because you can look it up all the time, anytime. Okay? Does that make sense? So why we care so much about electronegativity? So look at 2 different compounds, 2 molecular compounds. Well, not compounds. 2 molecules. I did not use the correct term. So this is the molecule of hydrogen. It consists of 2 hydrogen atoms. Now, let me make a disclaimer. When I ask you questions, unless I assign a difficulty level to a question, it's very easy. Like, it's almost stupidly easy. There are 2 hydrogen atoms in the molecule of hydrogen. Are they identical? Yes. Is one of them more electronegative than another? No. Remember that analogy of two brothers? These are twins, identical twins. They can't beat each other. They don't pull electrons away or towards. Make sense? So the electrons stay in the middle. They are, sort of equally distributed. Does that make sense? Now, electronegativity of hydrogen is 2.1. I think so. Anyway, 2.1. Electronegativity of chlorine is 3. So chlorine is more electronegative. What does that mean in relation to the ability, hunger for electrons? Chlorine is hungrier, right? So it's the analogy of like this chlorine is 12-year-old brother and hydrogen is 10-year-old brother. Are they going to share the Xbox? Yes. But electrons will be kind of shifted towards chlorine. And sometimes it is said that electrons spend more time around chlorine than they do around hydrogen, which kind of works if you look at the analogy. The 12-year-old plays Xbox 4 days a week, and 10-year-old plays Xbox 3 days a week. So it is shared, but unequally. Okay? So there is a general rule that says that if the difference in electronegativity between two atoms is less or equal to 0.4, the bond is nonpolar. If it's between 0.5 to 1.8, it is polar covalent. And if it's more than 1.8, like 1.9 and more, then it's ionic. Okay? I have a question which is like 2, maybe 3 out of 10 difficulty-wise. For which group of elements this rule may not work quite often? Think about what are the weird elements. We always say, this is always, and then there's an exception. There's an exception. Which group?
Group 1 or 17.
Transition metals. Transition metals are always weird. There's always something weird about them. Okay? I can give an example right now. Here's mine. Good. So here's the thing. Okay? So electronegativity of bismuth is 1.9. It's a transition metal. It is a metal. It's metal all right. Okay? Electronegativity of chlorine is 3. Okay? So let's say you have bismuth to chloride. Okay. So what is the difference between the electronegativities of bismuth and chlorine? 3 minus 1.9. What's the difference? 1.1. So based on that rule, the bond is covalent polar, right? But bismuth is a metal. And if a compound contains a metal, it's an ionic compound. So the answer is no, it is an ionic compound. The rule of metal being in a compound and defining it as ionic that rule trumps the electronegativity rule. Does that make sense? Okay? So, let's take a look at these bonds. So potassium and nitrogen. Since I don't remember, we're going to scroll back and forth. Electronegativity of potassium 0.8, electronegativity of nitrogen 3. What is the difference? So 2.2, that's the difference. Let me do this, hold on. So 2.2. What type, if it's more than 1.8, right? What bond type is that? Ionic. Nitrogen and oxygen. I happen to remember nitrogen is 3, oxygen is 3.5. What's the difference? 0.5. So first of all, ionic or covalent? Covalent, polar, 0.5. Okay? Two chlorines. Zero. Difference is 0, right? So, non-polar covalent. Hydrogen is 2.1. Chlorine is 3. The difference? 0.9. Polar covalent. Now, quick question, which is not for the exam, but for your sort of processing of this chemical concept. So we have two bonds, NO and HCl, right? Which bond is more polar?
D.
Yeah, because the greater the difference, the more polar the bond, okay? So we're not going to go into the weeds on that, but we're going to start discussing like very basics of what determines the shape of the molecule, okay? So the methane, which can be represented by this Lewis structure, is actually not a flat molecule. There's a atom of carbon in the center, and 4 atoms of hydrogen are located at the corners of the figure that's called tetrahedron. Okay, I don't know, when I was a kid, I don't know if you guys saw it. When I was a kid, in like Soviet Union, we had milk and half and half that was sold in paper containers that had exactly that shape. Okay? So, here's the big story. What predicts the shape of the molecule? To answer this question, it's actually very simple. Bonds, chemical bonds, in covalent compounds, what are they made of? What constitutes a bond? What is here? A pair of what? Electrons. What charge do electrons have? Negative. Charges of the same sign, what do they do? No. If we have two negative charges nearby, are they going to attract or are they going to repel each other? They're going to repel each other. So kind of, I don't know. Again, so think of negative charges hating each other. They want to be as far from each other as possible. Does that make sense? Is that clear? So let's use this image that we have on the screen right now to illustrate it. So if you look at the Lewis structure, okay? of methane. If you assume, just assume, that this is the actual shape, that it's flat and hydrogens are sticking out it's a plain molecule, right? That makes sense? What's going to be an angle between two bonds here? What kind of angle is that? 90 degrees, right? It's a right angle, right? So 90 degrees. But the question is, can we make this angle greater? Can we move bonds in a way that they are farther from each other than 90? The answer is yes. If we get out of the two-dimensional plane and enter the three-dimensional space, does that make sense? So, for instance, we're going to talk more about the wedge dash representation of molecules, but I will give you sort of a primer on what it means. When in this specific type of formula, the bonds are presented by a line, they are in the plane of the screen. That makes sense? The wedge means that this hydrogen kind of sticking out towards you. The dash means that this hydrogen goes behind the screen. If you look at this 3D model, you can see that now it's a three-dimensional molecule, not plane. Does that make sense to you all? And the angles are going to be 109, which is more than 90, which is good. It means that this bond is farther from the neighbor than in this representation. Okay? So this is the actual shape of the methane molecule. So this table here summarizes different shapes. I'm going to demonstrate on some of them how that happens. So they actually use some. We already did. Okay. First of all, carbon dioxide. Carbon, how many electrons on the outer shell? 4. Oxygen, how many electrons on the outer shell? 6. So carbon needs 4 more to be happy, right? And it gets them from oxygen. That make sense? So now, carbon had these 4 electrons originally, so all carbon electrons are shared. Make sense? Oxygen, on the other hand, shared only 2 of its electrons. It has 4 more. Clear? That make sense? So these are bonds. Now, what do we call these guys? These guys called, and it's an official name, it's called a lone pair. What do you mean? Oh, okay. Yeah. So if you think about, this is how you can represent this the other way. Look, carbon forms 2 bonds to each oxygen, right? Each oxygen has 2 lone pairs. I can guarantee you there is no other way to place these bonds in these lone pairs so that they will be as far from each other, farther than they are here, okay? So this angle is 180, and these angles are approximately 120. Sounds good? Now, this is the simple example. What about a more complicated one? We already discussed methane. Now I want to talk about ammonia and water. So let's take a look at ammonia. So the formula is NH3. Right? All good, everybody? How many electrons does nitrogen have in the outer shell? 5. Okay? And hydrogen has 1. This and this. So we have 3 hydrogens. That's your Lewis structure. So far, are we clear? So we can write down this. Clear? So we have 3 bonds and a lone pair. If I represent this molecule like this, these angles, what are they going to be? 90. Is that optimal? Can we increase the angle? We can. Okay, now take a look. Here's your nitrogen, right? What if we put 1 hydrogen here, 1 here, another one there, and the lone pair is going to be right here. So effectively, it's like a pyramid. Okay? I usually represent it this way. Take a look. Can you see my fingers? So my fingers represent 3 bonds that are looking down. The rest, like my palm, is the nitrogen atom. And the lone pair, invisible lone pair, is right here. So this way, these angles become 109, which is more than 90, which is great. Am I making sense? But now, if you think about water, if you ever looked at the representation of the water molecule in textbooks, it always is represented like this. Did you ever think why we don't do this? Why is this wrong? Why is this conceptually wrong? Well, how many electrons, does oxygen have in its outer shell? Dude. 6. Yes. Hydrogen is 1. Okay? Good. So we can change the representation into this. 2 lone pairs. So 2 lone pairs at oxygen and 2 bonds. Right? So in this representation, the molecule is actually, like you have again 90 degrees, but again, can you increase the angle? And the answer is yes, exactly the same way. So what you need to do is to put oxygen in the center, direct 1 hydrogen here, another hydrogen here, and 2 lone pairs. Since I draw on the flat surface, I can't do that. Okay, but 1 lone pair will kind of stick out. So in front of the screen, and another one will be looking behind the screen. This is why the angle between these bonds is not 90, but approximately 109. Okay, sounds good? Why do we care? Because of polarity. You will see how important it is, like dead serious. So, molecules can be polar, molecules can be nonpolar. And I want to emphasize that a polarity of a single bond does not necessarily imply that the entire molecule is polar. For instance, take a look at your diatomic gases, like hydrogen or oxygen or chlorine or whatever, nitrogen. When you have a structure like this, these hydrogen atoms, are they the same? Yeah. Do they pull electrons in any direction? No. So, it's a non-polar molecule. Clear? Now, what about this? So carbon has electronegativity of 2.4. I'm going to make it larger. Okay? So carbon is 2.4. Oxygen has 3.5. What is the difference? 1.1. How would you classify each individual bond? I mean, is it polar covalent? Yes. Make sense? Okay? But the shift of electrons to the left and to the right, they cancel each other out. That makes sense? So overall, while bonds are polar, overall molecule is not, because these arrows effectively cancel each other. Does that make sense? Not a perfect example, but imagine that you are standing and two people pull on your arms, and they pull with equal force. You're not going anywhere. You're staying in the same place. Does that make sense? I created a better example, much better example. Imagine that they're not pulling on your arms. They're pulling on your pants horizontally. Your pants aren't going anywhere because the pulling force cancels each other out. Does that make sense? This is another example. So this is the what would you name this molecule?
Calcium.
Not calcium. C is carbon.
Carbon. Tetrachloride.
Yes. Very common organic solvent. So carbon is 2.4, chlorine is 3.0. What's the difference? 0.6. Yes, I'm an idiot. 0.6. Bonds are what? Then bonds are, remember, it's more than 0.4. So polar covalent. But it's an equal pull to four corners of the tetrahedron, so they are going to cancel each other out. In my pants analogy, three people pull it kind of down, not completely down, like to the sides, but a little bit down. Does that make sense? Like these three chlorines pull carbon pants to the sides and a little bit down, while this chlorine pulls pants straight up. And they are, they draw. It's even. Okay? So it is, despite the fact that all four bonds are polar, the molecule is not. Now, a simple example is, hydrogen chloride, HCl, right? So hydrogen 2.1, fluorine 3.0. The bond is covalent polar. Chlorine pulls electrons towards itself, so it's a little bit negative. Hydrogen is a little bit positive. These two slight charges do not cancel each other, right? So it's a dipole, we call it a dipole molecule. And it means that it is polar. Now, here's the comparison. So this is water, okay? Remember the shape that we discussed, that it's angled, right? So the electronegativity of oxygen is 3.5. Hydrogen is a 2.1. How would you classify each of these bonds? Polar, covalent, right? It's a polar bond. Make sense? So who's going to play Xbox more? Oxygen or hydrogen? Oxygen. Oxygen is going to pull electrons towards itself because it has greater electronegativity. So there's going to be slightly negative charge on oxygen and slightly positive charges on hydrogen. Okay? Now, it doesn't matter which direction the arrows go, but using our pants analogy, oxygen's pants are being pulled down by two hydrogens. See that? Not exactly down, but kind of down. And nothing cancels it. So pants are going to go down. So this molecule will actually be a dipole. So one end is going to be slightly negative, and another end is going to be slightly positive. Contradictory to that, carbon dioxide. Each bond is covalent polar, but these arrows cancel each other out. Am I making sense? Right? Is that clear? I can't read minds, so I try to follow your facial expressions, but if you don't give me any signs, I have no idea. So another example of a polar molecule is ammonia. So this nitrogen, lone pair does not have any pooling, and effectively nitrogen has an electronegativity of 3. Each hydrogen has an electronegativity of 2.1. So each bond is covalent polar, but these arrows, these pens down forces don't cancel each other out. There is nothing that would compensate. So ammonia is the polar molecule. Why do we care? This is the great rule. Polar dissolves polar. Nonpolar dissolves nonpolar. Am I making sense? Good? Clear? So, I'm going to give an example. If you will try to dissolve carbon dioxide in water, it dissolves very poorly. Carbonated drinks, what happens when you open the bottle? Well, hopefully not, but it's like, psst, right? Because during, when Diet Coke is made, they force CO2 in the solution by the increased pressure. The minute you open, it's not really soluble, it escapes, because solubility is actually pretty low at normal pressure, okay? Now, carbon monoxide, this compound, on the other hand, pretty interesting molecule to begin with. Oxygen has electronegativity of 3.5, carbon is 2.4. Each of these bonds, how would you classify it? Polar covalent. oxygen is going to pull electrons towards itself, is this molecule will be polar. More electrons on. Is there any compensation? No, right? There's no compensation. There is one way electrons are shifted. Can you see that? So it's a polar molecule. Water is polar solvent. What would dissolve in water better? Carbon monoxide or carbon dioxide? Monoxide. How is that relevant? Do you have carbon monoxide detectors at home? That's your answer. Carbon dioxide is, what is the main component of human blood? How does blood look like? Liquid. What's the main component of blood? Water. It's water. Main component of human blood is water. Carbon dioxide is poorly soluble in human blood. Carbon monoxide is soluble at a much better level. Therefore, carbon monoxide poisoning can happen even when carbon monoxide concentration in the air is relatively low. Does that make sense? So, let's determine the polarity of this molecule. This is very, like, it's a pretty cool oxygen. How would you name it first? Name it for me. Oxygen, then difluoride. Okay? Make sense? Oxygen difluoride. So first of all, let's take a look at the polarity of a bond. The difference in electronegativity is 0.5. So it's a polar covalent bond. Now we need to make a Lewis structure. Okay? Now they don't really talk why this is the shape of the molecule, but you can imagine, like, remember oxygen, it has 2 lone pairs and 2 bonds to fluorine, right? In order to make the best distances between all of them, these angles got to be 109. So all in all, the shape of this molecule is going to be like this, actually shown here. So there it is bent. Make sense? What is more electronegative? Oxygen or fluorine? Fluorine. Right? So electrons are going to be shifted towards fluorine. So oxygen spans being pulled down and nothing compensates it. Right? So there's going to be slightly positive charge on oxygen, that end, slightly negative charge on that end, that are not compensated. So it is a dipole, it's a polar molecule. Am I clear? So the reason why this is, in addition to what we discussed, it's important to understand what can be dissolved in water, for example. So HCl is the polar molecule. It can be dissolved in water. The solution of hydrogen chloride in water, we call it hydrochloric acid. Make sense? And just to give an example, at normal temperature, like room temperature, and normal pressure, 1 liter of water can dissolve 300 to 400 liters of HCl. The gas. Okay? These dipole attractions become incredibly important when we start looking at the formation of hydrogen bonds. Take a look at this. So I'm gonna lead with water. So we have two water molecules, right? Am I clear? Oxygen, because it is more electronegative, has a slightly negative charge. Hydrogen has a slightly positive charge. Agreed? Positive and negative charges do what? Attract. So this is the hydrogen bond. This is how hydrogen bonds are formed. You observe the same hydrogen bond between two molecules of ammonia. Now I'm going to ask you like a theoretical question, not really. So if you have nitrogen, I'm going to do like simple structure. That's ammonia, right? Nitrogen is more electronegative than hydrogen, agreed? It is true, so slightly negative charge here, slightly positive charges on hydrogens, right? And then we have water molecule. Okay, good? Everybody agrees with what I just put on the screen? That there is a little bit of a negative charge on oxygen, a little bit of positive charges on hydrogen. Do you follow my train of thought? So these guys, can they form? Yes, they can. Hydrogen bonds are extremely important in nature. Okay? Question for you. If you will take a cotton cloth, right, and pour some water on it, what's going to happen to the cloth? It's going to absorb it. Water is going to bind to the material from which this cloth is made. Do you agree with me? Cloth is made of cotton, so mostly it's cellulose. Cellulose is polar. Water is polar. Water literally forms hydrogen bonds with molecules of cellulose. If you take this, the skillets like that, like special skillets that, not cast iron, another one like Teflon kind of thing, non-sticky, what do you, yeah, non-stick, yeah. If you put water in it, it's going to form a little nice like bubble instead of spreading around, because the surface of that skillet is very non-polar. Water is polar, so they do not interact with each other. Am I making sense? So hydrogen bonds in nature effectively are responsible for the shape of DNA and play a very important role in shaping proteins. So these forces, these interactions, the dipole interactions, the hydrogen bonds and dispersion forces, they are interactions between molecules, not within a molecule. Am I making sense? We're going to finish this unit and take a break. So dispersion forces are holding nonpolar molecules only, exclusively. Okay? So imagine that you have two nonpolar molecules. Okay? So in this nonpolar molecule, just by chance, randomly, like fluctuations, sometimes the distribution of charges becomes uneven. So the molecule for a short period of time acquires a positive charge on one end, a negative charge on another. Again, it's not permanent. It's not like water molecule that is polar all the time. So it's temporary polarity, let's call it this way. If two molecules form this very short-lived temporarily dipoles, they can interact. This is called the dispersion forces. Are they strong? Absolutely not. So if you compare the strands, the bonds, and it's not really fair comparison, the strongest bond that can be formed is between two ions. Ionic bond is the strongest. Covalent bond, whether it is polar or non-polar, is the second strongest. And then you have intermolecular forces. So hydrogen bonds are stronger than the bonds between dipoles. And specifically why we call this a hydrogen bond, because it is formed between a slightly positive hydrogen and something else. If it's not a slightly positive hydrogen, it's a dipole. Right? If hydrogen does not participate, it's a dipole. And then dispersion forces are the weakest. So we're going to walk through this, and then I'm going to mention why both hydrogen bonds and dispersion forces are actually quite important. So let's start with, we're going to name, and then we're going to say what interactions are likely to be present between the molecules. So name the compound. Nitrogen trichloride. So is it a polar molecule? Chlorine pulls nitrogen bonds down. Is there any compensation to pull them on top? No, so it's a polar molecule, right? So you can represent this molecule as dipole, a little bit of a plus, a little bit of a minus. Does it have any hydrogens? Two dipoles, can they interact? Yes. So like this, right? Sorry. Okay, one dipole, another dipole. Okay? So they will interact. If no hydrogens are involved, it's a dipole-dipole interaction. Okay? Water. I'm skipping naming, obviously. Is it a polar molecule? Yes. Is hydrogen involved? Yes. What kind of bond? Hydrogen bond. Bromine. This bond, is it polar? Dude. Two equal atoms. None of them is stronger than another in terms of the electron attraction. Does that make sense? Non-polar. There's no polarity in there. What type of forces between non-polar molecules? Is that ionic? Is that dipole? Is that hydrogen? It's dispersion. Dispersion force, yes. Potassium chloride.
Waiting on y'all to say it.
Okay. Potassium chloride. What type of bond is between potassium and chloride? There you go. Ammonia. Is it a polar molecule? So remember, nitrogen, two hydrogens, so bonds are being pulled down with no compensation from the top. So it's a polar molecule. Is hydrogen involved? What type of bonds? The reason why hydrogen bonds and dispersion forces are so important, they're weak, but their strength is in numbers. We already kind of, discussed the hydrogen bonds in nature. Have you seen geckos? Like in a zoo? The lizards? No? Okay, nah, commercial is not going to count. Yeah, you saw geckos. When they're like the glass terrarium, can they walk up the glass? Can they walk up the glass ceiling? Yeah, because they have very interestingly constructed limbs, whatever, toes, call it whatever you want, and they form dispersion forces. There are so many tiny little projections that despite the fact that those forces are weak, the gecko can still, there are enough interactions to hold the animal. Make sense? And this is actually an example why they have to be small. They would be heavy, they would drop. Okay? Questions? Let's take a break.